Alright, getting into the rationals. Let's finish these last two, and then we'll get on to the sign chart stuff. Alright, so we've got a rational. It looks like it's like a degree 2 on the top, a degree 2 on the bottom. Remember, the degree is just the largest exponent of the numerator, and the largest exponent of the denominator. We'll talk about just polynomials, tell you the degree, right? So there's a polynomial on the bottom, there's a polynomial on the top. And the degree of each one is going to help us determine if there's a horizontal asymptote or if there's a slant asymptote. The vertical asymptotes are going to come from the factors in the denominator. Speaking of which, that's pretty much always the first thing you'd want to do, right? When I see this, if you can factor, you always do want to factor, right? So let's see what happens. Here you've got a difference of two squares. X squared is a perfect square, 4 is a perfect square, so that's going to factor into conjugates. X plus 2 and then x minus 2, right? It's really nice. Difference of two squares factors into the conjugates. Remember, you always check to see if you have factored something correctly by foiling it back together. Multiply it out. X times x is x squared. You have a plus 2x, then you have a minus 2x, plus 2, minus 2, that cancels. That's why there's no middle linear term, right? When you have conjugates, when you multiply them out, the middle two terms cancels, which is why this looks, I think it's so clean. And then, yeah, the negative 2 times the 2, that's 4. All right, so always check to make sure you factor it right, because if you don't, everything else is wrong. It's like, thanks for playing, but try again. Anyways, nothing is going to reduce, right? This factor, x, doesn't reduce with anything in the denominator, so there's not going to be any holes. Remember, the holes come from a factor that reduces from the numerator and the denominator. So let's go ahead and start filling some stuff in. I know these two factors left over in the denominator are going to give me vertical asymptotes. This factor, set it equal to 0, x minus 2 equals 0 means I'm going to have an x or a vertical asymptote at x equals 2. And remember, asymptotes are lines. So if you just put 2, that's wrong. 2 is a number. You need a line. X equals 2 is the vertical line at 2. So this factor gives me the asymptote at x equals 2. This factor gives me the asymptote negative 2. I don't know why. Sometimes I do the 2's like this. Sometimes I do it like that. Literally makes no sense. It's just completely random. Let's graph those asymptotes. 1, 2. Remember, I like to do asymptotes with these dotted lines. Cool. So let's see. Horizontal asymptote or slant. You will never have a rational that has both. That's either going to be one or the other, and that's just going to be based on the degrees. Since the degrees are the same, what you're going to do is end up looking at this ratio of the coefficients. If you don't know, by the way, if you don't know your horizontal asymptote rules, you should pause this video, go look them up, and then remember them, because those horizontal asymptote rules, you were taught them in Algebra 2, you should have been taught them last year in Precal, and then you definitely are going to need to use them periodically in calculus, right? So when the degrees are the same, you find the ratio of these leading coefficients. So I got a 1 on the bottom, 3 here, so 3 over 1, that's 3. So the horizontal asymptote, remember it's a line, so you need y equals, and it's y equals 3. If the top is bigger, there would not be a horizontal asymptote, and there would be a slant. We'll see that in the next example. So if the top is bigger, the answer for horizontal would be none, and then you have to figure out what the slant or what the oblique asymptote is. When they're the same degree, you look at the ratio of the coefficients. If this denominator would have been anything larger than a 2, so if the bottom is bigger, that's when your asymptote is y equals 0, the x-axis. So bottom bigger is when it's 0. If the ratio is the same, or if the numbers are the same, then it's wherever that ratio tells you, right? So here it's 3 over 1. So here my horizontal asymptote is going to be at 3. And then if the top is bigger, there's none, which we'll see on the last one. So know those horizontal asymptote rules. Here there's none, right? It's either going to be one or the other. You will never have both. Okay, so let's see. Everything else, let's just try to get the graph. The x-intercepts come from the zeros, which come from the factors in the numerator. Here you've got the factor of 0. So I think just the origin, right? This factor, x, tells you have an intercept at the origin. Ooh, and look, it's squared, right? That's the multiplicity of 2. Remember, multiplicity is how many times that root or that factor repeats. Here it's going to repeat twice. And if you remember, there's behavior at those roots based on the multiplicity. An even multiplicity means this graph is going to bounce, or it's just going to touch the x-axis. It could do something like this, where it touches the x-axis and then it exists on the negative side, or it could do something like this, where it touches the x-axis but it exists everywhere else on the positive side, right? We know it's going to either go down towards the asymptote or up towards the asymptote, because your graph always trends towards the asymptotes. But we need to know whether it goes up or whether it goes down. We know it's even multiplicity, so it's going to bounce, not cross, but we need to figure out whether it's bouncing in above or bouncing in below. So you just need a test point. Like, how about 1? Like, I'm going to plug in x equals 1, and I'm going to figure out, do I get a positive output, plot the point up here, or do I get a negative output? And you could plug it in to either the factored version or into the original not factored version. Either way is fine. I'm just going to go back to the original, and I'm just going to plug in 1 for x. So 1 squared would be 1. 3 times 1 would be 3, right? So if I were to plug in x equals 1, I'm going to end up getting a 3 on the top. Let's see, 1 squared would be 1. 1 minus 4 would be negative 3. So look at that, right? If I plug in 1, I would end up getting out a negative. You don't really have to plot the point. It doesn't have to be super precise, but that point being negative tells you that graph exists beneath the x-axis. Since it's an even multiplicity, it cannot possibly cross and go up. Since it's an even multiplicity, this graph is just going to bounce, touch the x-axis, and then it's also going to stay negative. If you want to check, you could always just plug in another number. Like, you could plug in -1, but it's going to give you out a negative output. So when in doubt, plug in x values, figure out where the points are, then you can graph it. But once you know 1 and you know the multiplicity so it bounces, you can kind of get the rest. Okay, we still need the rest of this graph, right? The graph is either going to exist up above the horizontal asymptote or down below the horizontal asymptote. Same thing over here. The graph either could be up above in this area, or maybe it's down below. Now, logically, you don't really have to do a whole lot here, right? If you want, you could do a similar process. This is x equals 3, so you would need to test a point to the right of 3, and then you need to test it, or no, sorry, the asymptote was at 2, that's my bad. You need to plug in an x value to the right of 2, and then to the left of -2, and that will tell you whether you have a bigger number, you know the y value will be up here, that kind of tells you it's up in that upper quadrant, or if you have some small positive number or negative number, tell you like this. But just think about it, right? If I potentially thought the graph existed down beneath the horizontal asymptote, think about what would happen with the graph, right? If it's down below, I know it would come towards this vertical asymptote, then it would come over towards the horizontal asymptote. Well, that means you would cross the x-axis again. And if you cross the x-axis again, I would have had another x-intercept. But if I had another x-intercept, I would have needed another factor in this numerator. I know the only factor up here is x, which tells me the only x-intercept is at 0. It happens twice. That's why it's got the even multiplicity and it bounces. If the graph would have existed down here, you would have needed another factor in the numerator. So logically, I know it is not possible for the graph to be in that area. Therefore, it must, sorry, my staple is kind of making this difficult for me. Therefore, you know the graph must exist up above. Again, if you wanted to plug in something like 3, take 3, plug it in, you're going to get a y value that's above the horizontal asymptote. You can always plot the points, but logically you can kind of just connect the dots and then get them done. Same thing over here. If you thought the graph was down beneath the horizontal asymptote, it would cross the x-axis. Like if you thought it was something like this, it would cross the x-axis again. That cannot happen because you don't have any other factors. Therefore, the graph has to look like this. And guys, pay attention to the words, right? It says sketch. I'm not going to be like grading your graphs and like trying to pull out like a millimeter ruler and trying to make sure everything's super precise and perfect. Sketch means get the general shape right. Get the important characteristics done. So get the asymptotes in the right spot, get the intercepts in the right spot, and then generally the shape needs to be correct. Doesn't have to be point for point super precise, right? Just get it done. Anyways, we still need the y-intercept. You can do this kind of two ways. You can just look at the graph, or if you want to look at the equation, for the y-intercept, you would plug in 0. So I'd have 3, 0 squared. So I'd have a 0 on top. and then you'd have 0 squared minus 4, 0 minus 4 is negative 4, but 0 divided by 4 is 0, right? It's kind of cheating. If you know the x-intercept is 0, then you get the y-intercept for free, right? Because this point, the origin, it is simultaneously the x-intercept and the y-intercept, right? Really nice. You get both of them at once. All right, so there's the first rational function. Let's finish this last one, and then we'll put a wraps on this graphing part. All right, first thing, of course, is to factor. Here I can factor out an x from both terms. So I have x plus 2 over x minus 1. Nothing reduces, right? If you have any factors that are the same, you would reduce them, you'd have wholes. But here we don't. So let's go ahead and try to get some important characteristics. This factor tells me a vertical asymptote at x equals 1. These two factors are going to tell me my x-intercepts. You're going to have one at 0. If you want to write x equals 0, and if you want to write x equals negative 2, that's fine. I just kind of like writing them as coordinate points. So this one tells me the x-intercept of 0. This one tells me the x-intercept of negative 2. Oh, and look, that's the origin, right? So I know that's also going to be the y-intercept. You could always plug it in. 0 squared plus 2 times 0. All right, so 0 plus 0. That's 0 over negative 1. So that's 0. It's a little bit of cheating. If you know this one's an x-intercept, you also know it's the y-intercept. All right, so let's go to the degrees and let's compare them. Here the degree in the numerator is 2, the degree in the denominator is 1. Now remember, the degree is the largest exponent, not necessarily always the first one. Typically they're written in the nice descending order, so it is the first one that you look at, but not always. Sometimes I may be mean. The degree is always the largest exponent, so just be careful. But here the degree in the top is bigger than the degree on the bottom. So this one is not going to have a horizontal asymptote. It will instead have a slant. It will have an oblique asymptote. And how you find it is you just do division. And I'm going to find it by doing long division this time. So let's take the numerator. Don't forget your placeholder. Let's divide it. Remember, that's the numerator and then the divisor. Or the denominator. Here we go. But that's your dividend and your divisor. So x minus 1. Okay, so dividend, divisor, you're going to have a quotient, potentially a remainder. The remainders aren't important here. A couple different ways to think about it. If you need a review over long division, go look it up. You should know how to do it. But I always like to think, how do I make this match this? Well, I would need to take an x, multiply it by an x. So x times x, that's x squared. X times negative 1, that's negative x. And then I always put the parentheses first, because the next math you're going to do is subtraction. If you don't put the parentheses, you may forget to distribute the negative, so be careful. But you figure out how many times does x go into x squared? X many times. You think, hey, x times what equals x squared? And then this question mark, you line it up above the like term in the dividend, and there you go. And then you're going to subtract, but parentheses first, then you subtract. This minus this cancels, right? Why does it cancel? Because we picked this to be important, so that it would factor, right? We needed those terms to cancel. All right, then we have 2 minus negative 1, 2 minus negative, so that's going to cancel, and you have, well, not cancel, it's going to add negatives, you're going to plus. So I got 3x, and then since I canceled one, bring down the next one, right? You always have a binomial, so if I have two terms that you're dividing with, you always need to be working with two terms. Oh, only a minute. I don't think I'm going to finish. Oh my gosh. Oh well. How many times is x go into 3x? 3. Multiply this times this. This times this. Parentheses first. Then you subtract. Those cancel, minus negative. So your remainder is 3. Okay. So when you're doing the long division, remember, you think, what can I do to make this match that term, or to make this match the next term? And then you have to multiply. Then you put that term in the kind of in that next little column. Then you subtract. Make sure you put your parentheses before you subtract. When you're doing the long division, the remainder doesn't matter, right? That's the dividend. This is the divisor. This is the quotient. That's the remainder. Remainder doesn't matter. The only thing that's important for these slant asymptotes is this quotient. So y equals x plus 3 is going to end up being that slant or that oblique asymptote. All right, I'm going to need one more video to finish up this, so I'll be right back.